Hello everybody and welcome to our first programming lecture of our lecture series Data Formats and Preprocessing. In this lecture you will learn how to handle DICOM files in Python. To fulfill this task we use a subset of CT images provided by the Cancer Imaging Archive or TCIA. The peculiarity of these scans is that they only contain a single slice. This means that we start to explore DICOM files in a two-dimensional setting. To make things easier for you, we already provide a sample file in a corresponding course directory. However, if you want to obtain the full dataset, you can simply download it from Kaggle by following the link in the provided notebook. Alright, let's get started by importing the necessary libraries. At first, we import a library called pathlib, which greatly simplifies working with paths. The second library, and the most important one in this notebook, is called PyDICOM. PyDICOM allows us to work with DICOM files in Python. Last but not least, we import matplotlib to visualize some images. Now we are ready to read our first DICOM file. To perform this task, we define a variable called DICOM_file and then use the readFile function provided by PyDICOM. So we access the PyDICOM library and call read_file. The readFile function accepts the path to a DICOM file as its argument. In our case, as the DICOM file lies directly next to the notebook, we can simply provide the name of the file. Congratulations! You just loaded your first DICOM file. To receive the DICOM header, you simply need to print the DICOM file. As you can see, it returns a bulk of information, including the manufacturer of the scanner, the image shapes, and many more. To extract an individual entry from the DICOM header, you need to know its unique identifier. As an example, the identifier, which describes the number of rows in an image, is 0028 0010. To access this entry, you need to access your DICOM file and then use those two identifiers as an index. In fact, you need to convert those values to hexadecimal first. So to come back to our example, we need to convert 0028 to the hexadecimal 0x0028. We perform the same operation for 0010, so again we write 0x0010. And as you can see, this returns the number of rows in this particular DICOM file. Another, more comfortable way is to access the rows attribute stored in the DICOM file object. We access our DICOM file once more, but instead of using the unique identifier, we want to get access to the rows attribute. And you can see that even the autocompletion directly proposes rows to us. Note that when you use this method to access elements in the header, you lose the information about the unique identifiers and the corresponding descriptor. Last but not least, it is time to extract the actual image out of the DICOM file. Let us store this image in a variable called CT, and then we access our DICOM file once more and call the pixel array attribute. The pixel array always contains the actual image. To visualize this image, let us quickly create a matplotlib figure and then call plt.imshow, where we pass our CT image. Additionally, and this is important, you should change the color map, because if you don't change the color map, the resulting image will look like this. And this somehow doesn't look like a typical CT image. To solve this problem, we simply pass cmap equals to gray or cmap equals to bone. Both of those strings will yield really nice results, and it is really up to you to decide which one you like better. Now we extracted a beautifully looking CT image out of this DICOM file. Cool! Now, after learning how PyDICOM works and how we can use it to load a single DICOM file, it is time that we take a look at our first real-world three-dimensional example. In fact, we will inspect a head MRI scan provided by Sinudo. We again provide the dataset in the corresponding directory. So, let's get started. At first, we need to define the path to the head MRI scan. Instead of using a plain string, we are going to create a path object. As we used a path object to define the route path to the head MRI, we can use the glob function to return all items in this directory which correspond to a provided pattern. As an example, if you would want to retrieve all files in a directory with the file ending .dcm, you could simply pass star.dcm, and the glob function would then return the path to all files in this directory with this particular ending. In this case, the files do not have a specific file ending, so we simply return all files stored in this directory. Let us create a variable called all_files, and then we access the path to our head MRI scan and call .glob. To return all files in this directory, we use the star or asterisk sign. Note that as the glob function returns a generator, we need to convert the output to a list to be able to inspect all paths. Now we can take a look at all files. And as you can see, we have now a list containing the paths to all DICOM files in this directory. Perfect! That's exactly what we need. We are now able to read those files by using the readFile function from PyDICOM and append them to a list. At first we create a list called MRI_data. Then we loop over all paths in all_files and read the DICOM file defined by the current path. We can store it in a temporary variable called data and use PyDICOM.read_file and pass the current path. Next, we simply need to append this data object to our MRI data list. As some of you may have noticed, the paths above are not ordered. Therefore, it may be possible that the DICOM files are also not ordered according to their actual image position. We can verify this by inspecting the slice location for each DICOM file. To do so, we inspect the slice location of the first 5 elements in MRI data. We can simply print the slice location attribute. As you can see, the slice locations are indeed unordered, which would mean that our complete scan would be shuffled and useless. We can sort those files by using the Python internal sorted function. The sorted function expects a list, which it should sort as its first argument, and a function which extracts the element to be sorted by as the second. In Python, we should at first define a new variable which stores the sorted list, as an example MRI data ordered, and then we call the sorted function, pass our MRI data list as the first argument, and a lambda function which extracts the slice location for each element as the second or key argument. Let us quickly copy the code snippet from above to verify that the slices in MRI data ordered are sorted correctly. Perfect! As you can see, the slice locations are in order now. We can now extract the actual data from the sorted DICOM files and store them in a list. Let us create a list called full_volume Then we loop over our MRI data ordered and append the pixel array of the current slice to our full volume. Now we can take a look at some slices of the ordered 3D volume. To do so, we will create a 3x3 subplots figure. At first, we define our figure and axis objects and then call plt.subplots, where we pass the number of rows and the number of columns. Additionally, we can pass a figure size argument to increase the size of the figure. Let's simply use 10 by 10. To keep track of the slices we want to plot, we define a slice counter variable which we initially set to 0. Now, to be able to access the current axis objects, we use a double nested for loop in the range of 3. This allows us to use I and j to access the current axis object. Now we simply need to call .imshow and extract the corresponding image from our full volume. Additionally, we choose a different color map. Let's use gray. Last but not least, we simply need to increase the slice counter by 1. This grid visualizes the first 9 slices from the head MRI, starting from around the neck region. Awesome! We now have a way to handle 2-dimensional and 3-dimensional data stored in the DICOM format. But as you will have noticed, manual file reading and ordering seems kind of tedious, and it would be great if there would exist a tool which handles this for us. And in fact, there is such a tool. Its name is SimpleITK. SimpleITK provides functionality to automatically detect and read all DICOM files in a directory without the need of manual file reading or sorting. The overall routine is always identical. At first, you need to get the series IDs of all files in a directory. This is important as often multiple scans are stored in the same directory and we don't want to mix them. Then we need to grab all file names in the directory which have our desired image ID. The third step is to define an image reader and pass the file names extracted in the previous step. Last but not least, we execute this image reader to get our desired images. Alright. At first, we import the necessary library, so we import SimpleITK as SITK. Then we grab the series IDs by calling sitk.imageSeriesReader.getGDCM series IDs. Here we pass our root path to the head MRI. Note that SimpleITK is a C++ library which cannot handle pathlib objects. Therefore, we need to convert the path to the head MRI to a string. Let us take a quick glimpse at how the series IDs look like. You can see that in this case, the function returned a tuple containing only a single series ID. Next, we extract the series file names by using sitk.imageSeriesReader.getGDCM series file names. The first argument for this function is again the path to the head MRI scan, whereas the second argument is the desired series ID. Let us also take a quick look at the file names, and we can see that the files are already sorted. Alright, now it is time to define the series reader by calling sitk.imageSeriesReader. To pass the file names to the series reader, we call our series reader and then access the setFileNames method. This method accepts the series file names as its argument. Last but not least, we finally load our image data by calling seriesReader.execute. This is all you have to do to get the full volumetric data. The final step we have to perform is the conversion of the returned SITK image to a NumPy array. This can be done by calling the getArrayFromImage function. So we define our final variable called head MRI and call SITK.getArrayFromImage, where we pass our just loaded image data. We can take a quick look at the shape to verify that it is identical to the shape above. Great! Now we can simply copy the code snippet from above to have a final look at our images. We simply replace full volume by head MRI. Congratulations! You have now all the tools you need to work with DICOM files in Python. Thank you!